What's up, everybody? It's Miss Brothers. Hey, let's go through practice number 8. So here we are in Unit 8. This is practice number 8, stoichiometry, conversions where we're converting volume to volume of another substance. All right, so we are starting off with number 1 right here. And we are focusing on this problem right here, which is I have 1 mole of nitrogen gas, otherwise known as N2. It's reacting with 3 moles of hydrogen gas, and when these things react together, they end up giving us a product of 2 moles of NH3, and NH3 is otherwise known as ammonia. We'll just write that right there. So then we go to our question. What we're trying to figure out is that if we, what volume of hydrogen, so what volume of this, is necessary to react with 5 liters of nitrogen to produce ammonia, which again is this product right here. Now, the difference between what we have up here and what this problem is asking for is quantities. So right now, you guys, we are dealing with quantities that are in moles, and our problem is asking us for quantities in volume. And remember, you guys, volume, the unit that we're using is liters. That's how we know that we're trying to find the volume of something. The unit tells us that. All right, so let's go ahead and figure out, like all of these type of conversion problems, we have to start with what we already know or what we have. We've been given 5 liters of nitrogen, so we're going to write that right over here, 5.0 liters of N2. And we're going to set up what's essentially our column A on our T chart. And remember, you guys, column A is what we've been given. Now, the next thing we have to do, because we're dealing with molar quantities here, it means we have to get this quantity to moles first. So let's do that. So we're trying to get our final unit of nitrogen to be moles of N2. And remember, you guys, if we're dealing with the volume of any gas, the 1 mole of that gas is going to be equivalent to 22.4 liters of that gas. In this case, our gas is nitrogen. Now what we can do is we can go ahead and cancel out our liters of nitrogen here, and we're left with moles of nitrogen. So we're not quite done yet because we've got to do equivalencies. So we have to be able to cross out moles of nitrogen because eventually we're trying to get to our liters of hydrogen. So what we have to do in there's our B column, in our C column is about going back to the equation and using our equivalence ratios here. So according to this problem, I have 1 mole of N2, and I know that because I don't have a coefficient, and if I don't have a coefficient, it's the same as saying 1 of something. Okay, so I've got 1 mole of nitrogen, and in this problem, my equivalent ratio is that I have 3 moles of H2, and I got that 3 from this coefficient. Remember, you guys, the coefficient essentially tells us how many moles of something we have. We have 3 moles of H2. So now what we can do, we can go ahead and cancel out our moles of nitrogen gas right here and here, and we've done that. Now remember, ladies and gentlemen, that we are trying to finish with a volume of hydrogen, which means we need liters of hydrogen. So we have to be able to get rid of this moles of hydrogen, so we're going to take 1 mole of H2 down here. And remember, you guys, our equivalency is this. If we have 1 mole of any gas, in this case the gas is H2, that it's going to be the same as saying 22.4 liters of that gas. So now what this leaves me, it leaves me with the ability to cancel out this unit of moles of hydrogen here and here, and now all I have to do is I have to do my math across this. So I'm going to take 5.0 times 3 times 22.4 liters of H2. And I'm going to divide that by whatever I have left on the bottom. So I have 22.4 times 1 is 22.4. And if I do the math on that, we'll go ahead and do that so you can see my calculator doing its thing here. We've got 5.0 times 3 times 22.4 equals 336. And we're going to divide that by 22.4. And that leaves us 15, and don't forget our units, liters of H2, and that is going to be our final answer for problem number 1. So again, you guys, we're just going through that process of figuring out what are we given, how many moles of that, what's the equivalent ratio using our chemical formula, making any last-minute conversions that we have to in order to get to the correct unit, and then, of course, getting our final answer. Okay, so let's go ahead and do number 2, and we're going to go through that same process again. So it's asking us what volume of ammonia is produced in the reaction in problem 1. So what we figured out in this first problem was how much hydrogen we need in order to make ammonia if we're given 5 liters of nitrogen. So now what we're trying to do is, if we have 5 liters of nitrogen and 15 liters of hydrogen, how many liters of ammonia are we going to end up with? So in order to start this, what we're going to do is we're going to start out with this same 5.0 liters of N2. So we're going to go through the same process, but now we're trying to solve for ammonia instead of trying to solve for hydrogen. All right, so I've got 5.0 liters of nitrogen. That's what I'm given. That's my A column. And I'm going to go through and do this exact same thing like I did up here. 1 mole of N2 is the same as saying 22.4 liters of N2. And I know I'm going to put this 22.4 liters of N2 at the bottom for the simple reason that it allows me to cross-cancel out liters of nitrogen up at the top. I'm going to go back to my chemical formula, because remember, you guys, I have to do my molar ratios now. And again, I have to get rid of this mole of N2, so I'm going to come up here and realize I have 1 mole of N2. Now, unlike the hydrogen, where we used 3 moles of hydrogen in our first problem, in this problem, because we're trying to solve for our volume of ammonia, we're going to use how many moles we have in this original formula. And up here, we have 2 moles of NH3. So now what we have the ability to do, we have the ability to cancel out our 1 mole of nitrogen gas here and our mole of nitrogen gas here, and we're left with moles of ammonia. So far, so good. But we're not quite done yet, because remember, we're trying to find the volume of ammonia, not the number of moles. So we know that this unit has to be in liters. So we're going to come up here and go liters of NH3 right here, and 1 mole of NH3 or ammonia right here. And we remember that if we have 1 mole of any gas, it's going to be 22.4 liters. And now what we have is the ability to cancel out our unit of moles of ammonia here and moles of ammonia here, and we're left with 5.0 times 2 times 22.4 liters of NH3 over, and again we've got 22.4 times 1 times 1, that's going to make 22.4. And if we do the math on this one, we've got 5 times 2 times 22.4 equals 224, divided by 2, and that equals 10 liters of H2. Oops, I'm sorry, that's not H2. That's supposed to be NH3. My bad. I got caught looking up there, and I shouldn't have been. I should have been looking right there. All right, good. So far, you guys were off to an excellent start. So let's go ahead and look at our next problem. So we're using a new formula now. We're using this formula, and so we're done with our formula from above. We're now using a new formula. It says if 20 liters of oxygen are consumed in the above reaction, how many liters of carbon dioxide? And if you guys, just a quick reminder, carbon dioxide is CO2. Carbon dioxide. Just wanted to make a quick reminder so we know what our words mean. Are produced. So we are given 20 liters of oxygen, and we have to find out how many liters of CO2. That's what we're trying to finish with. So let's go ahead and start with our 20.0 liters of O2. Okay. And again, you guys, we have to get rid of this, so we know we're going to have to convert to moles first, because that's what we do in our B column. So 1 mole of O2, and because this is a gas, is the same as 22.4 liters of O2. Okay, now we have the ability to cancel out liters of O2 here and here. And remember, A column is what we're given, B column we're converting to moles. In our C column, we are going back to our molar ratios that we have to figure out in this problem right here. Now we have moles of O2 right here, so we know that this is going to be moles of O2. And according to our problem, we start with 5, because that's our coefficient, so we start with 5 moles of O2. We know that we are trying to get to liters of carbon dioxide, but we don't have liters yet, but what we do have is we have moles of carbon dioxide. So moles of CO2, that's going to be the unit we want to finish with, CO2. And according to our chemical equation, we start with 3. So now that we have this information, this gives us the ability to cancel out our unit of moles of O2, and we're left with moles of CO2. So we're almost done here, because we have to be able to cancel out moles of CO2 and finish with liters of CO2. So we're going to put liters of CO2 as our final unit up here, and moles of O2 right here. And what we know is that if I have 1 mole of O2, it's the same as saying 22.4 liters of any gas. In this case, the gas is CO2. So now this gives me the ability to cancel out moles of O2. Oops, that's supposed to be CO2. Oh, sorry. I just caught that as I was writing it. Moles of CO2. My bad, you guys. So now I can cross that out, which leaves me liters of CO2. Whew. All right, so now all I have to do is multiply across here. So 20.0 times 3 times 22.4 liters of CO2. CO2 over 22.4 times 5. Now, if I do that, we're going to go ahead and again, you guys, one of the most important things you can do is to do all of your math above and below before you do your division. So we're going to go ahead and do all of your multiplication first. So if I take 20 times 3 times 22.4, that equals 1,344 liters of CO2 over 22.4 times 5 is 112. And if I do the math on that, 1344 divided by 112 is 12 liters of CO2. And I'm going to circle that. Hooray. Okay. Let's jump into problem number 4. Now, number 4 is a little bit tricky, and I just want to make sure that we're compensating for something. And we'll do that here in just a minute. But let's start. Here we have 2 moles of hydrogen are decomposing to give us products of 2 moles of hydrogen and 1 mole of oxygen gas. Okay. Now, please notice the problem, you guys. It says if 30 milliliters of hydrogen are produced in the above reaction, how many milliliters of oxygen are produced? So we start with 30 milliliters of hydrogen. Now, you have a couple different ways you can do this, and let's start with the way that I think is easiest. Now, you'll notice, you guys, that we are dealing with milliliters of hydrogen, but remember, we can't do this until we convert this unit to liters. Because remember, you guys, if we're dealing with volumes, what we know is 1 mole of any gas equals 22.4 liters. And what we have right here is we have milliliters instead of liters. So technically, you guys, you can add another column to this, and I'll show you what I'm talking about. So you start by giving 30 milliliters of hydrogen gas. So, and in this case, you guys, it's just hydrogen, okay? But the thing is, we have to convert this to liters first. So our first, in this one, you guys, our first conversion is not to moles. We have to actually get milliliters to liters. And so this is how we're going to do it. What I need you to remember, you guys, is that if I have 1 liter of something, so 1 liter of H in this case, is the same as saying 1,000 milliliters of H, because H is R. Because remember, you guys, milli is the prefix that means 1,000. So if I have 1 liter of hydrogen, it's the same as saying 1,000 milliliters of hydrogen. And see, now what this does is this gives me the ability to eliminate this right here, okay? This unit of milliliters of hydrogen, we can eliminate that, and we're left with the the ability to go with liters of hydrogen. So that's the first move that we have to do in this one. Now that we've done this, we can convert liters to moles. So, and again, you guys, if we have liters of something and we need it to convert it to moles, so 1 mole of hydrogen is the same as saying 22.4 liters. So that kind of gets us back on track with something like this problem up here. So in this A column, we did, again, what we were given. In the B column, in this one, we had to first convert to liters. Now in the C column, we can convert to moles. So now, again, you guys, we're dealing with hydrogen. So now I have the ability to go ahead and cancel the unit of liters out, and I'm left with moles of hydrogen. So I cancel out liters of hydrogen. Okay. Now, in my D column, I have to go back to my problem and do my equivalencies. So what I want to know is how many milliliters of oxygen. So just know, you guys, we are actually going to have to go back to milliliters eventually, but not just yet. This one's going to be a really long, fun one. You'll see. All right, so the first order of business is we have to go back to our molar ratio because we're trying to get rid of moles of hydrogen. And in our problem, we have 2, or I should say our equation, we have 2 moles of hydrogen. And what we're trying to do is we're trying to figure out moles of oxygen. In this problem, we have 1 mole of O2. Right, in my chemical equation. There it is right there. There's no coefficient, which is the same as saying there's 1 of them. So now what we can do is we can cancel out our moles of hydrogen. Boop, away you go, and boop, away you go. So now we're left with moles of O2. And so we're going to go ahead and go through that same process that we always do. If we have 1 mole of O2, it's the same as saying we have 22.4 liters of O2. So you say to yourself, yes, that's it, we're done, that's as far as we have to go, that's as far as we've ever had to go. Except in this case, you guys, look, what are they asking for? They're asking how many milliliters of oxygen. So I know that my final unit has to be milliliters of O2. All right? And if I have liters down here, 1 liter of O2 as the same as saying 1,000 milliliters of O2. Whew! So we've got a lot going on here, but I've got some good news. We can do some canceling, which means we can do a little bit less math as we go along here. So what we're going to do is we're going to go along and look for numbers that we can cancel. So obviously we can cancel any number that's 1, but look, you guys, I can actually cancel out this 1,000 right here and this 1,000 right here, which means I don't have to worry about mathing it out later. Okay, so hooray for me. So what's left, you guys, is I've got 30, and I've got 1, 1, 1, and I've got 22.4. And the last thing I have is milliliters of O2. Okay. And over that, I have, looking down here, I've got 22.4. And I've got 2, and I've got a bunch of 1s. I'm not going to worry about that. So if I go ahead and do my math on this, let's go ahead and do that. Bring my trusty calculator here. I've got 30 times 22.4 equals 672 milliliters of O2 over 22.4 times 2 is 44.8. And let's see what my final answer is on this. So that's going to be 672 divided by 44.8 equals 15 milliliters of O2 gas. And that is exactly what we end up with. So yeah, there's a lot going on in this problem, you guys. And again, the big thing is that we had to convert this to liters, and then we eventually had to convert our liters back to milliliters. So this one proved to be, there's a lot of different things going on. And again, you guys, this is one of those problems that, oops, I forgot to cancel out some units in here. Sloppy work, brothers, very sloppy. This would not have been a 5-point problem. And that just kind of goes to show you how quickly things can get away from you in a big problem like this. So, not my best work, but again, we live, we learn, we make mistakes, we fix them. So, but anyway, there's a lot going on in that problem, and that's why this one took a little bit longer. And now we are ready to do number 5. All right, number 5, you guys, we have 2 moles of carbon monoxide, CO, combining with 1 mole of oxygen gas, and it produces 2 moles of carbon dioxide gas. So let's go to our question. It says, how many liters of carbon dioxide are produced if 75 liters of carbon monoxide are burned in oxygen? And then it asks a second question. How many liters of oxygen are necessary? So let's go ahead, you guys, and I'm going to do this problem mathematically, and then we're going to do it conceptually. All right, so let's go ahead and do it mathematically first. Let's start out, because this is what we're practicing here. So we want to know how many liters of carbon dioxide. So that's what I'm trying to figure out are produced if we are given 75 liters of carbon monoxide. Carbon monoxide, mono meaning 1, so that's this first one here. So we've got 75 liters of carbon monoxide, otherwise known as CO. That's our given. That's what's in our A column. And then we're going to go through our regular processes. We're going to start by converting this to moles. So 1 mole of carbon monoxide is the same as saying 22.4 liters of carbon monoxide gas. And that gives us the ability to cancel out our liters of carbon monoxide. Then so that's our A, there's our B column, here's our C column, means we're going back in to find our equivalent ratios of carbon monoxide and carbon dioxide. And according to this, now remember I have to get rid of moles of carbon monoxide first, so I'm going to put that down here. And according to my problem, I have 2 moles of carbon monoxide, and I've got 2 moles of carbon dioxide. And that's what I'm going to put right here. And that's going to give me the ability to cancel out my moles of carbon monoxide here and here. And again, you guys, I'm trying to figure out how many liters of carbon dioxide I have. So I need to go ahead and put 1 mole of CO2 down here at the bottom. And remembering that if I have 1 mole of any gas, it's going to be 22.4 liters of that gas. Okay. And when I get done doing all of my math, I've got 75 times 2 times 22.4 liters of CO2 over 22.4 times 2. And once I do my math, what I end up with, and I can go ahead and show you the math here on the calculator real quick, I've got 75 times 2 times 22.4 equals 3,360 liters of CO2 over, and that's going to be 22.4 times 2, 44.8. And if I do the math on that, it's going to be 3360 divided by 44.8 equals 75. Well, look at that. 75 liters of CO2. Now, technically, you guys, we really didn't have to do any math on that. And here's what I'm talking about. Because I've got 2 moles of carbon monoxide here, and I finished with 2 moles of my new substance, my CO2 here, which means that I have equal quantities of each. So if I think about that in terms of how many liters, if I start out with 75 liters and my chemical equation shows me that I start out with and finish with equal quantities of each, I can automatically say to myself, well, if I have 2 here and 2 here, that's equal quantities. If I don't even have to really convert everything. I simply know that if I start out with 75 liters of one, I'm going to finish with 75 liters of the other. So like I said, I could do the math to prove that thinking was correct. Now, with that said, you guys, let's talk about how many liters of oxygen are necessary. And again, you guys, I don't even really need to do math for this, because I can go into my equation and I can say, well, if 2 of these is the same as 2 of these, then I only had 1 mole of these, which means I only need half as much oxygen to react with this carbon monoxide in order to get 2 moles of carbon dioxide. So really all I have to do is just say that 75, half of 75 is going to be 37.5 liters of O2 is enough to make that. So that's the second part. And if you want to, if you want me to show you the math on that, all you have to do is you would just say, all right, well, 75 divided by 2, which is half, is 37.5. All right, so I don't want you to get too caught up in that. All I need you to understand is that you really do have to look at these ratios, because sometimes you don't necessarily need to do math in order to figure out these quantities. So this is good practice, and most of what we are going to be doing in this class is going to require you to do this sort of step. But just know that there are ways for you to kind of think around that if you have to. All right, so there you go. That is your first practice with stoichiometric conversions when we are converting from the volume of one substance to the volume of another substance.